Good afternoon, students. Let me start the class now. In the previous class, I was discussing about how to encode the given message using Shannon's basic algorithm, which he proposed many decades before. And there we had a procedure of converting the decimal fractional numbers into binary numbers, because our probability is always between 0 and 1. So naturally it is a decimal fraction. Now that has to be converted into binary. So I thought, let me revise some basics of how to convert a fraction number into binary. If you have studied it in PUC, or if you have studied it in first year of BE, that is fine. You will have to recall it now. Even if you have not studied it also, you can learn it now also. It's a very simple method. So converting decimal fraction to binary, convert this n, for example 0.6875 to radix 2. The solution is multiply n by 2 repeatedly and collect the integer bits. In the integer conversion, we keep on dividing by 2, and then we go from bottom to top and arrange those bits. That is called double method. But in the fractional conversion, we multiply by 2 and we go from top to bottom for arranging those bits. It is just the reverse of whatever we did in the double method. So if you have to convert 0.6875 multiply by 2, you will get 1.375, and that integer point, write it separately. The integer part, write it separately. Take only the fraction now, 0.375. Now multiply 0.375 by 2 once again. You will get the integer portion 0. Keep this 0 here. Now take the fractional part again, multiply it again by 2. You will get 1.5. Take the integer part 1 here, and that 0.5 again multiplied by 2. You will get 1. Take the integer part, then you get the fraction 0. That is where the conversion ends. Now, at times the conversion may end, at times the conversion may not end. It depends on the type of the number. For example, this 0.6875 is in the form of 2's power in the negative exponent. So if any such number which is already there in the power of 2 with negative exponent, then the conversion procedure will stop, which means we will arrive at 0 at some point of time. But for some numbers, we may not get 0 at all. That is when Shannon told that particular condition of ni in between those two left and right extremes, because we have to come to a decision of an integer number there. Sometimes the decimal fraction, when it's converted to binary, it may go on for a never-ending number also. It depends on that particular number. If it is not in 2's power, then it may not end at all. So stop when fraction is 0 or when enough fraction bits are obtained. Now we have to take a decision how long we have to keep on doing this procedure, because some number may not end at all. We may have to take a decision that let us stop it where we have a near accurate conversion. So in this particular case, n is 0.6875, which is 0.1011 to the base of 2. If you want to check it, you can check it always. It is 2 to the power of minus 1 plus 2 to the power of minus 3 plus 2 to the power of minus 4 is 0.6875. This is a simple procedure. Next, let us say we have a number which is 0.188. Observe this number. This is not a summation of 2's powers in the negative exponent. So this conversion may not end at all. We only have to end it at some point of time. So let us say 0.18 into 2, we get 0.376. Here take this integer portion, that is 0. 0.376 into 2, we get 0.752. Again integer portion is 0. 0.752 into 2 is 1.504. We get that integer portion 1, we keep it here. Now that 0.504 into 2 is 1.008. We take the integer portion 1. 0.008 into 2, it is 0.016. Now here it is 0. Now if you continue this way, 0.016 into 2, 0.032 you will get. 0.03 into 2, you will get 0.064. There again you will keep getting 0, 0. and this conversion process may never end. We may not reach 0 in the fractional part here anytime. Now in such a case, we should actually get what? If at all this has to end, then we should get 1.0 there. Whenever we multiply something, we should get 1.0. That means somewhere previously we should get 0.5. But in this particular case, we may not get it at all. That means the conversion may not end so easily. So what we can do, we have taken 5 significant digits and we have written an approximate answer. The last example now, 0.625. Now you already know this is in 2's power with the negative exponent. It's a summation of 2's powers only. So we can easily get it now. 0.625 into 2 is 1.25. Integer portion is 1. 0.25 into 2 is 0.5. Integer portion 0. 0.5 into 2 we get 1. The integer portion 1 is here. We end it with 0 now. So it is 0.101 is nothing but 2 power minus 1 plus 2 power minus 3 equals 0.625. So it is actually 0.5 plus 0.125 is 0.625. 0.5 is 2 power minus 1. 0.125 is 2 power minus 3. That is when I was telling, if the decimal fraction is a summation of any of 2's powers in the negative exponent, then only the conversion process will stop somewhere. Otherwise, it may not stop at all. We have to take a decision when to end it. Now, let me stop sharing this slide. I showed you this slide only to remind you about how do we convert decimal fraction to binary fraction. Now, let me share the PDF. Okay, let me continue. In the morning, we were discussing this particular exercise and I was telling you that we should get this binary expansion of the fractions. And we get 0.4 to the base 10, we convert it into binary, we get 0.01. 0.4 into 2 is 0.8, 0.8 into 2 is 1.6 and we already have this 0 and 1. That 1.6 also 0.6 into 2 again 1.2, it can go on that way. But it is not required for us here. Why? Because Shannon has told us already that 2 bits are sufficient. Just recall this particular procedure here. The particular procedure where Ni should be less than or equal to Lg of 1 over Pi and it should be less than 1 plus Lg of 1 over Pi. So in our particular case, I showed you this tabular column in the morning. 2 bits are sufficient for us because probability is more, number of bits can be less. That is how we are taking a decision to stop it at 2 bits. Similarly, 0.65 we have to convert it at least up to 3 bits because we have got that Ni as 3 for this particular probability. Similarly, for 0.8 it is up to 4 bits. For 0.92 it is again up to 4 bits. Just I will come back to this tabular column. You can see 2, 2, 3, 4, 4. So that way we have got 2 bits here, 3 bits here, 4 bits here, 4 bits here. In the very first case, anyhow it is 0, so it is 2 bits here. Which means for the very first message which is having the highest probability, we can keep the code as 00. Then for the next one we keep the code as 01. Then the next code as 101, then 1100, then 1110. I will come back to the tabular column now. Now I hope you have understood all this now. The fraction is converted into binary and that binary's integer portion is completely discarded and we get this code 00, 01, 101, 1100, 1110. Now let me annotate this. This is, even though it is a simple procedure, this is one of the great findings of Claude Shannon in the previous century. I should tell you a special thing about Claude Shannon now. One particular university in USA had appointed Claude Shannon for the research purposes and the university had given him full-fledged lab facility, full-fledged assistants for housekeeping and full-fledged swimming pool and garden for him. Whenever Shannon wants to relax, he can relax in the swimming pool, he can relax in the garden, and whenever he is hungry, he can order for food. There will be people exclusively taking care of one person called Claude Shannon. The university had recognized the brilliance of this particular scientist, and it had given him a full-fledged campus support, and he was staying inside the campus only for months together and for years together. And whenever he was inside the lab working for all these things, the university used to ask him when he will come out of the lab, and he used to give some dates in advance. When he used to give these dates in advance, the whole university students as well as the professors were waiting for that particular day when Claude Shannon is going to come out of the lab and when he is going to reveal his latest findings in the information theory concept itself. So people used to eagerly wait, and on the day when he used to tell the dates, on that particular date he used to come out of the lab, and in the auditorium he used to present his latest findings for the complete staff as well as students. That was the greatness of Claude Shannon. Just like in the Indian context, if at all, let us say, some great saint is meditating inside a cave, eagerly other people, his students or his disciples or the general public who are his devotees, they'll be eagerly waiting for the person to come out of the cave so that he will reveal his latest revelations or the divine interventions to the public. In the same way, in USA, people were waiting for Claude Shannon's latest findings. The great scientist passed away in 2002. We still admire him for all his discoveries or invention or methodologies. Right now, all these procedures may seem quite simple for you, but he was the one who worked exhaustively for finding out these concepts, and now we are using all these concepts in our communication systems. I have been telling always in the classes that a transistor is the 8th wonder of the world and mobile phone is the 9th wonder of the world. Even though we call it as a mobile phone, actually the mobile phone is nothing but a computer and a communication device in your palm now. We can easily call it as a palm top computer. It is not just a computer, it is a communication tool as well. It is not just a communication tool, it is a personal digital assistant as well for you. You can take photographs, you can send messages, you can store photographs, you can save files, you can save these notes also in your mobile phone. You can do everything inside your mobile phone now. If it is only a computer, all that communication aspects are not possible. But in the mobile phone, whatever you are doing along with the computer, that also can be done in the mobile phone. Sending mails, receiving mails, sending messages, everything is possible. Communication is possible, storage is possible, entertainment is possible. You can store music there, you can keep listening to music. What is not possible on the mobile phone now? So, if mobile phone is doing all these wonders, there is a contribution of Claude Shannon also for the development of this particular product. That is why I keep saying transistor is the 8th wonder of the world, mobile phone is the 9th wonder of the world, and Google Earth itself is the 10th wonder of the world. In the Google Earth now, or in the maps, in the Google Maps now, you can see any place on Earth so easily. You can locate it through the satellite pictures. You can have a satellite picture mode or you can have a normal map mode. Wherever you want to go elsewhere, you can easily find out a route map, and the Google auntie will keep on giving you instructions that to take left in 200 meters, take right in 400 meters. That is actually an artificial voice. The Google auntie is giving you instructions. There is no lady they are giving instructions. Actually, it is a completely synthesized artificial voice. Just like this Siri. Siri, Alexa, they are all basically not a person's voice. They are synthesized artificial voice. That is complete digital synthesis. Now in all these inventions, there is a hard work or a heavy hard work of so many scientists. There are so many scientists who worked in the last century, so that in the present century we are enjoying all the discoveries as part of our communication, as part of our computation, as part of the real life products as well, including entertainment using radio and television. So I thought you should appreciate Claude Shannon again and again for whatever way we are using them in our real life. Okay, let me continue with this exercise now. Now you can see, just as he mentioned in his algorithm, we are getting for the message which is having the highest probability, we are getting the least number of bits. And for the message which is having the least probability, we are having the highest number of bits. Which means, if at all we go for fixed length coding, then for all these 5 messages, we may have to allocate 4 bits each. Unnecessarily, we are going to waste some resource. Instead, right now you can see, for sending S2 and S1, the first 2 messages with the highest probability, we are using only 2 bits. Now you may ask, out of 0001, again 2 more combinations are there. 1011 is there. Why are they left out? You may ask. Now, they are not left out as such. We have only 5 messages here with this probability. So we have such combination of codes. In future examples, you will see that if at all we have more number of messages with the distribution of probability, even those 2 codes will also be utilized in some examples. Similarly, a 3-bit code, only 101 is utilized. If it is a 3-bit code, we have totally 8 combinations. Right now, we are using only 1 combination. That is because of the reason that we have something called entropy also. We can't simply randomly use any type of code to any type of message. We cannot do that way. We have to take care of the probability as well, entropy as well. That is why, using the Shannon's algorithm, we are getting this type of coding strategy. I hope now you have understood the method of arriving at a code for a given message with the given probability. Anyhow, we have one more next example also. The next example, the first part you only are going to work out and you are going to tell me the answer. I am going to give you some 2 to 3 minutes time. By that time, you only have to finish this particular tabular column. Because next example, there are only 3 symbols there. And you can easily do it. Let me see how fast you will be able to do it. Now let me continue to the next part of this particular exercise, where we have to find out the efficiency. So, for finding the efficiency, first let us find the entropy of the source. Entropy of the source is the summation of Pi into Lg of 1 over Pi. So, we have 5 messages there. When we compute the entropy for the source, we get 2.098 bits per symbol. Now, this is source entropy. If we have to find out the coding efficiency, now we have that particular term where I mentioned about the H cap of S. That is where we have a summation of number of bits in a code along with its probability. So that is the average number of bits per symbol. Now this is the average number of bits per symbol in the encoded sequence is given by Hn cap equals 1 over n summation of I equals 1 to q ni into Pi. So please remember, this is the average number of bits per symbol in the encoded sequence. Don't confuse this with the H of S. H of S is the source entropy. That is also the bits per symbol only, but it is the average information content per symbol. H of S or entropy is the average information content per symbol, which is expressed again in bits per symbol. But when we encode it now, we want to find out the coding efficiency now. So the average number of bits per symbol in encoded sequence is given this way. Let me show you the summation here. H cap of S equals summation of I equals 1 to 5 of Ni into Pi. That means the very first code is having only 2 bits. Probability is 0.4. The next message is having 2 bits. Probability is 0.25. Next it is 3. next 4, next 4. So multiplied by their respective probabilities, we get this h cap of s equals 2.55 bits per symbol. Now we can easily find out the efficiency as eta c. The coding efficiency eta c is the entropy of the source divided by the average number of bits per symbol. So h of s divided by h cap of s, that is 2.098 divided by 2.55, that is 82.27%. If it is 82.27%, there is something called redundancy. Redundancy is R eta c, that is, we expect that the efficiency has to be always 100% or we expect the efficiency to be 1. What we expect is h cap of s and h of s have to be same, but that is an ideal situation. We may not have such ideal coding methodology at all. So there is something called redundancy, that means 1 minus efficiency, 1 minus eta c, that is 17.73%, which means that the coding which we have performed right now using this Shannon's algorithm is about 82% efficient and it is about 18% deficient. In the sense, about 18% of the redundancy is still there in our coding system, in this particular coding system, and nearly 82% efficiency is there. So the goal is to have minimum redundancy and maximum efficiency. By means of any coding algorithm, if we can increase the efficiency and reduce the redundancy, then it means that with the minimum number of bits, we are sending out maximum number of information and our purpose is served. So here n equals 1 as the sequence length is not specified in the problem. In this given exercise, we have assumed it to be 1 over 1 only. You can see here that h cap of s, we have considered only one message, one symbol that way, because it is not given there. It is not given that this is having sequences. So we have taken n equals 1. Now the next exercise you only have to do now. Exercise 2 is design a source encoder for the exercise 14 in chapter 1, where we had a source which was in 2 states emitting symbols A, B and C. We had worked it out in the earlier chapter. Compare the average output bit rate and efficiency for the coder for the block size n equals 1, 2 and 3. Now that n equals 1, you do that. Remaining 2 and 3, I will show you the solutions here itself. So I will go back to that particular page where this exercise 14 is there. And there I will tell you for A, B and C what is the respective probability. Now you follow the procedure which was told here till now and you worked out immediately and then you tell me the answer. Let me see how many students will really respond to this particular query. So exercise 14, I think it is in page number 37. I will directly go to that page number 37. Yeah, this one. This is that exercise 14. A discrete ergodic Markov random process is represented this way. It is in 2 states emitting symbols A, B and C. Now you have to find out the probability of A, probability of B, probability of C, which we have already done earlier. Okay. A gets emitted from state 1 again when it is coming back to state 1. So the probability of A is 3 by 4 into half. And the probability of B is again 3 by 4 into half. Whereas the probability of C is 2 into 1 by 4 into half. That is, we have already done this exercise here. Where is that? Messages of length 1. So we have already done it. P of A is half into 3 by 4 is 3 by 8. P of B is half into 3 by 4 into 3 by 8. P of C is half into 1 by 4 plus half into 1 by 4 because C is emitted twice. So it is totally 1 by 4. Now you have these probabilities. I will annotate them. You have the P of A, then P of B, then P of C. Now, follow that Shannon's encoding algorithm, make a tabular column there, quickly work it out and tell me the answer. Arrange them in the order of decreasing probability, then find out Ni, then find out fraction, convert the fraction into binary, and then tell me the codes. If you want any help from me, you just ask me in the chat box itself. Or else at least note down these values. P of A is 3 by 8, P of B is 3 by 8, P of C is 1 by 4. Now note down these values. I will go back to the page. I will show you the exercise of the first one. And based on that, you arrange in your notebook there quickly and you show me the answer. I will go back to the page where we were working it out. Yeah, this was the exercise which we worked out in the morning. Now it is 3 by 8, 3 by 8 and 1 by 4 for A, B and C. Now you arrange those as per the procedure and tell me the codes for these three symbols within the next 3 minutes. I'll keep on watching the chat box. Kuldeep has given the answer 010111, but no, two codes cannot be same. You have got the same code for both A and B. That is not possible. There is something wrong in the procedure. Go through that. Okay, now Kuldeep has given the answer 000111. 1, 1. Okay, let us see. Let us see whether any other student is going to give the answers. Well done, Kuldeep, but let us verify the answer after some time. What about the other students? Vanilla, Kavin, Indrajit, Manideep. You'll have to try out. Whenever class is going on, you should always have a calculator along with you and you should have a notebook along with you. Unless you work out, you will not be able to understand any of these things. Okay, no one else is giving the answer. Let me proceed. Manideep has given the answer 0, 0, 0, 1, 1, 0. Let us see. There can be multiple solutions here. It depends on how you take those bits there, whether you write it as ABC or BAC, both are possible because A and B both are having the same probability. So you can write as ABC also, you can write as BAC also. Okay, let us see the answer according to my solution. Now N1 is calculated. No, I have to go to the problem now. Let us say for n equals 1, I have arranged it as ABC itself, 3 by 8, 3 by 8, 1 by 4. So, for 3 by 8, we should have, according to the same rule, we should have Ni in between Lg of 1 over pi plus, at the left side it is Lg of 1 over pi, at the right side it is 1 plus Lg of 1 over pi. So, for all these three cases, we get Ni as 2 only. Now, when we take a fraction, first one is anyhow 0, 0 plus 3 by 8, 3 by 8 plus 3 by 8 is 6 by 8. Now, 6 by 8 plus 1 by 4, you will get unity only. So, now when you convert it into fraction, you will get 0, 0, 0, 1, 1, 1, according to my arrangement of symbols. So, it is 0, 0, 0, 1, 1, 1 and it is matching with Kuldeep's answer. But in case of Manideep also, it is 0, 0, 0, 1, 1, 0. That is also a good code and that depends on how you arrange it. If at all you arrange it as BAC, then you may get some other different answer. Or how do you get different? Here it is same, no? Even if you arrange it as BAC also, you will get the same answer. Why? Because it is 3 over 8, 3 over 8 and 6 over 8. So, I don't know how Manideep got this particular answer of 0, 0, 0, 1, 1, 0. Okay, just verify that we cannot simply assign some bits for each code. It is not a random way of allocating codes. We are actually going to compute the codes. Otherwise, if this exercise is very simple, we can simply give 0, 0, 0, 1, 1, 0, 1, 1 that way also. If the one more D is there and if at all they are all getting Ni equals 2, 2, 2, 2, then we don't have to go through this algorithm at all. Simply we can give 0, 0, 0, 1, 1, 0, 1, 1. All codes are distinct only. That doesn't matter. But next problem is we will have to have a block size of n equals 2 and we will have to have a block size of n equals 3. You remember the same exercise where we had written a tree diagram and using the tree diagram for sequences of AA, AB, AC, we had computed the information rate. And even for AAA, AAB, AAC, for the 3 symbol sequence also, we had computed the answers there. Now in the exercise, I am going to show you the other 2 now, n equals 2 and n equals 3. Now in this particular case, h1 cap is 1 over 1 summation of I equals 1 to 3 of ni into pi. So we are getting 1.5 plus 0.5 is 2 bits per symbol. This is the average number of bits per symbol in the encoded sequence. Now let us go to the next part, n equals 2. In this n equals 2, messages, we have to write them in the decreasing order. I am taking the same results which we had computed earlier. We have this AA, BB, AC, CB, BC, CA and CC. You will have to refer to the notes later on, in whichever page this particular exercise is there, that you have to refer later on. I have listed all those probabilities here now in the decreasing order. So when we have this particular calculation, I am not showing you the procedure here. When we have this particular calculation of finding out the number of bits for the given probability, applying the Shannon's algorithm, we get 2, 2, 4, 4, 4, 4, 4. We did not get 3 anywhere here. Just observe this. We did not get 3 anywhere here, which means the probabilities are related that way. Now, fraction, first one is anyhow 0, then 9 over 32, add it with this, 18 over 32, add it with this, 21 over 32, that way go on. At the end, 30 over 32, and here you have 2 over 32, anyhow you are going to get 32 over 32, you will get unity there. Ultimately it means 0 and 1. Now convert this fraction, decimal fraction into binary. Here we get 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 1. Now you can see we have only 2 codes having 2 bits each, and we have 5 codes having 4 bits each, and we don't have any code having 3 bits, because probability and the number of bits are inversely related. That is how you can see the encoded bits here. This is a message having 2 symbols. Remember again that G1, G2, G3, and you remember that theorem. G1 will be greater than or equal to G2, G2 will be greater than or equal to G3, that way it goes on till H. Remember the theorem? Now, let us find out the average number of bits per symbol. H2 cap is 1 over n, that is 1 over 2, summation of all these number of bits in each code into its probability. We get around 1.4375 bits per symbol. What was our H1 cap? H1 cap was 2 bits per symbol. Now H2 cap is 1.4375 bits per symbol. This is in accordance with the theorem which we discussed at length before, which means if a sequence is having more number of symbols, then the information content per symbol gets reduced because they are statistically dependent. And that is how we can convey more, but we can transmit less when the sequence length is increasing. Today morning I gave an example of the bus and the tempo traveler, the car for the family trip. Now recall the same example, you will understand this. Lastly, for n equals 3, the message AAA has the highest probability, that is 27 over 128, and the message CCC has the least probability of 2 over 128. Please refer to the previous pages where we had worked out these probabilities. Now the number of bits for the code word of AAA is LG of 128 divided by 27, that is LG of 1 over pi must be less than or equal to N1 less than 1 plus LG of 1 over pi. So we get 2.245 and 3.245, in between it has to be N1. So naturally N1 has to be 3 because it can be less than or equal to. So it is not an integer at the left hand side, neither it is an integer at the right hand side. So we decide that n has to be equal to 3. In the same fashion, other code lengths are computed and now they are tabulated here. This is a much bigger tabular column. I may not be able to show you in one screen. Let me see if I can reduce. Yeah, now you are able to see. If you are watching your mobile, then you will have pain, but I can't help it now. Only for a few minutes, keep on watching if you are watching your mobile. AAA is 27 over 128, it is 3 bits. Similarly, BBB, that way it goes on till CCC. We get this number of bits as 3344444666, that way it goes on. Now we keep on adding the fractions this way from 0 till 126 by 128. And when we convert this fraction into binary, we get all these values. Finally, for the very first two sequences, AAA and BBB, we get the answer 000001. For other things, 4 bits, we are getting 0110, 0111, that way it goes on till 1100. For the remaining sequences from CBC till CCC, 110, 110 till 111111. Now, when you write these messages, you can always write BBB first, AAA next. It doesn't matter. Similarly, here you can write AAC first, BBC next, ACB next, BCA later, CBB first. You can keep on doing that. It doesn't matter there. Only thing is, for that particular message, you will get that respective code. Even if these codes are interchanged otherwise also, it doesn't matter much, because all of them are distinct codes only. There is no repetition of any code anywhere. You can watch that all the codes are distinct. We will not get the same code again. That is the genius of Shannon's algorithm. Now, similarly, for the 6-bit, you can see this is the answer. Now, we have got this code for 3 symbol sequences. Now, let me enlarge it further. Let us compute H3 cap now for the same exercise. H3 cap is 1.297 bits per symbol. This indicates that when the number of symbols in a sequence increase and when the symbols are statistically dependent, you will get bored if I keep on telling again and again, but I will keep on telling again and again so that you will remember this for the lifetime. Even if you get bored also, I don't mind. I like to keep repeating this again and again. Only then you will remember this. So, in a sequence containing statistically dependent symbols, when the number of symbols increase, then the average information content per symbol gets reduced, or the bits per symbol gets reduced. That is the advantage for us. Now we will calculate the efficiency of the encoder for the given block sizes by giving H equals Hn cap. There it was H of S and H of S cap. Here, as we have the sequence length, we are specifically writing H and Hn cap. We are simply giving a symbol E. As H is 0.8113, for the very first case of single symbol sequence, efficiency is 40.56%. For the 2 symbol sequence, it is 56.44%. And for the third sequence set, it is 62.55%. You can understand now that when the codes contain more number of bits, naturally the efficiency is increasing. If a complete family goes in a single bus, then the efficiency of the trip is increasing. Efficiency will be slightly reducing if they go into tempo travelers. Efficiency will be further reduced if all of them go in 10 cars. Whatever is the example I told you in the morning, remember that. That makes sense here. Lastly, this exercise indicates that the efficiency increases with the length of the sequence. Means when the length of the sequence is more, efficiency is more. With this finding or with this conclusion, let me end today's class. For the next classes, always be ready with the calculator and with the notebook adjacent to you, because we have further such very interesting methodologies in future also, and I will show you only one exercise about how to solve and the next exercise you only have to solve and tell me the answer. I expect that all my students are attentive in the class and all my students will respond back for a teacher's query. With this message, let me end today's class. See you again in the next class. Until then, take care and bye-bye.